Alright, so in this video we're going to be talking about photoelectron spectroscopy. Photoelectron spectroscopy is basically where you take a sample of matter or a sample of an element and you're aiming energy at it and you are removing the electrons. So either high energy UV or X-ray rays are aimed at a substance, and if the electrons absorb enough energy, they're going to be pulled off of the atom. So basically, if they can overcome the attraction they feel to the nucleus, they're going to be pulled off the atom. And that's called the photoelectric effect. So after that, a detector determines what energy level and how many electrons were ejected at that energy that you aimed at the substance. So basically, this is something that supports electron configuration. So this is what they look like, and we've got helium here, neon here, krypton here. And basically on the y-axis, you have your number of electrons, on your x-axis you have the amount of energy necessary to remove those electrons at that point. So this is one way that you might see it, and these little lines are just indicating there's big jumps in energy. So ionization energy is the energy needed for an electron to overcome that force of attraction. So that's the energy required to pull off one electron from the atom. So this is different depending on how far the electrons are from the nucleus. So the further they are away, so if we have our atom here, if they are located on higher energy levels, they're further away from the nucleus, which means their force of attraction is a little bit less, so those are easier to remove. When they're really close to the nucleus, or they're on lower energy levels, they are harder to remove because there's a greater force of attraction. So let's look at a PES. Okay, so when you are looking at energy, remember that energy is equal to Planck's constant times the frequency of a wave. So the energy given off in the PES will exceed the ionization energy. So basically it's higher than required to pull off the electrons. So these electrons also gain some kinetic energy, movement energy. And basically your energy is equal to the ionization energy required to pull them off plus the kinetic energy required to get them moving. So, or you could rewrite it like this. Don't think you're going to have to do anything with that information, but it's worth looking at. So basically when you look at the spectrum, the kinetic energy is what's actually being analyzed by the detector. So this energy, this amount of energy, is actually the kinetic energy gained by the electrons. But the more energy they have, the more energy that was required to pull them off. Okay, so when you look at this, you need to be careful about a couple of things. First of all, make sure you look at the x-axis and see which direction the energy is moving in. So when it's closer to here at this point, that's a higher energy level, and when it's here, this is a lower amount of energy. And it could be the opposite, so you need to just make sure you're looking at it to see. So on the y-axis, we have our relative number of electrons. Basically, every single peak that you have here corresponds to a sublevel and a configuration. So what you have to do first is you have to decide, okay, what's the first part of the configuration? Well, the electrons that are closer to the nucleus are going to be harder to remove. So it's going to require more energy. So right here, this is the peak that corresponds to the highest amount of energy here. These electrons would correspond to the electrons in the 1s sublevel because they're closer to the nucleus, so they are harder to remove. Peaks with a lower amount of energy are going to be the valence electrons because they are easier to remove. So if I look at the relative number of electrons and you look at the height of the peak, well, this one is higher. So since this one's higher and it's about 3 times as high, that's going to be a P sublevel. All right? So basically, the easiest thing to do is to find where the 1s electron should be and then just write your configuration from that point. So we have 1s2. So 2 electrons in 1s, then we have 2s2, and then the next peak should be the 2p, and then since it goes 3 times as high as this, 2p6, And then the next one should be, and since it's the same height as this one, it'll be 3s2. So this is my configuration for this element. So it's 1s2, 2s2, 2p6, 3s2, which makes sense. I've got 4 peaks, and then I've got 4 sublevels here where the electrons could be pulled off. So I've got my configuration. You could be asked, what is this element? So if it's in 3s2, that would be magnesium. So you could be asked that. You could ask what each peak represents. So the closest one to the nucleus will be the one that's at the highest amount of energy. They're harder to pull off. The valence electrons will be further away. You could also be asked where you think where you think the energy might lie on a different element. So if we're looking at, let's say, aluminum. Okay, aluminum. Well, okay, aluminum has 13 protons. And basically, you could be asked to compare different elements given a spectrum of another one. So magnesium has 12 protons. So when you're removing the electrons, magnesium has 12 protons to attract those electrons to it. Aluminum would have 13 protons. And then the next element would have 14, and so on. So as you go down the period towards the noble gases, you're getting more and more protons, which means those electrons are going to be more and more attracted to the nucleus. So if I could be asked, for aluminum's spectrum, what do you think the energy might look like for 1s? Or could you explain why the 1s peak would not be exactly the same amount of energy? Well, it's because as you increase the number of protons, you increase the nuclear charge. So you're increasing how attracted the electrons are to that nucleus. All right, so let's look at this one. Sodium has a total of 4 peaks in its PES. Energies and millijoules per mole are 0.5, 3.67, 6.84, and 104 respectively. Explain the existence of 4 separate peaks in the spectrum. Okay, so first of all, you know that every single peak you see here will correspond to part of the configuration. So for sodium, the configuration is 1s2, 2s2, 2p6, 3s1. So every time that you have a peak, you're pulling electrons off of a different sublevel. So that's why you have 4 different peaks. Then it says suggest the specific electron and subshells that correspond to each peak. Okay, well, I know that 1s2 is closer to the nucleus, so that's going to require the most amount of energy to remove those electrons because they're more attracted. So the highest amount of energy would be 104. Then the next highest would be 6.84. Then it would be 3.67, and then 0.5. All right, so which peak would you expect to be the largest? Okay, so largest or the tallest, okay? Tallest, okay. So, well, remember the height of the peak corresponds to how many electrons you have in it. So this one has 2, 2, 6, and 1. This would be the tallest right there. Okay, so neon has an electron configuration of 1s2, 2s2, 2p6. How many unique peaks should you expect to see? Well, 1, 2, 3. You should see 3 for each sublevel. Which electrons correspond to the largest energies? Well, the peak closer to the nucleus would be the largest energy. And which peak of the spectrum should have the greatest intensity? So basically here it's talking about height of the peak. So the one that should be the highest would be 2p6. Because there are 6 electrons in here, the y-axis corresponds to how many electrons you have. All right, so this is a mixture, and in the mixture, I just want to point out a couple things. I don't think you're going to see this on the College Board test or AP test. Definitely not going to see it on my test, but just in case, let's talk about it really quick. So right here, you have 1s peaks for fluorine, oxygen, nitrogen and carbon. So first of all, the height of the peaks should all be the same. They should all have 2 electrons in there, but the problem is it's a mixture, and it was given they have a different amount of abundance here. So the one that has the most abundant, so basically the one that has the highest percentage and has more in the mixture, should be the tallest. Normally, I really think you're just going to see one element at a time, but I do want you to notice something. The amount of energy for each of these 1s peaks is different, and again, that goes back into the nuclear charge. So as we go down the period towards fluorine, fluorine is, has the most number of protons, that one is going to have a larger amount of energy to pull off those electrons. All right, so another way you could see data is ionization energy. Okay, so ionization energy, you could be given this, and basically you're going to be looking at large jumps. Large jumps indicate something special. So we've got 738 for the first ionization energy, so that's the energy required to pull off 1 electron. Okay, the second you pull off the second electron, the third you pull off the third, and so on. So you need to look for large jumps. So this one, it doubled. This one, it more than doubled. And then this one, it went up by 3,000, 3,000, about 5,000. So really the first largest jump is really significant. It's important. There's a jump between the second and the third energy level. Okay, so that tells me that it's pretty easy to remove these 2 electrons, but it's harder to remove the third. So those jumps indicate that when it goes from this to this, it's much harder to remove that third electron, and that's because you've hit something that's basically more stable. So as I remove those 2 electrons, let's say if I move it, okay, if it's easy to remove 2 electrons, it's probably going to be in the second group, in group 2A. It's in group 2A because if it's easy to remove 2 electrons, it's probably going to have a +2 charge. It's not going to want to remove that third electron, because basically what happens after you remove those 2 electrons, you've hit a stable electron configuration. You've hit something that it's much harder to remove those electrons. So in group 2A, they all end in S2. It's easy to remove those 2 electrons. After that, it's much harder to remove the electrons. So that's why there's this big jump right here. So we would say that this would be in group 2A. Now, if you saw a large jump here between the third and the fourth electron instead, that would mean that it's probably in group 3A. If you saw a large jump between the fourth and the fifth, it would probably indicate that it was in the fourth group. So it really corresponds, those big jumps, it corresponds to what group it's probably going to be in. All right, so if we look at the 11th and the 12th electron, that requires a lot of energy, and if you look, there's a huge jump between the 10th and the 11th. Those are probably in the 1s sublevel because they're closer to the nucleus, because they have a greater force of attraction. All right, then it says predict the formula of a compound that contains whatever this is and nitride. Well, if it's in group 2, it has a +2 charge, probably. And if it's bonding to nitride, nitrogen has -3 charge, so it should be in this ratio when it bonds. So basically, when you're given this information, look for big jumps. Those big jumps right here indicate that it's harder to remove that electron. So if this jump is if these 2 jumps, or it looks like these 2 electrons are easier to remove, then it's probably going to have a +2 charge. If the first 3 electrons are easy to remove, and then the fourth is really hard, then it probably has a +3 charge. If only the first electron is easy to remove, then it probably just has a +1 charge. So look for those big jumps. That indicates where it might be on the periodic table. All right, and I'm going to stop there.